Welcome to another episode of Code for Thought. The supercomputer called Jean-Zay can be found on the campus of Université Paris-Saclay, about 60 kilometers south of Paris. In June this year, 2023, I made my way there to meet with Nathan Cassereau and Hatim Bourfoune, who both work at IDRIS. IDRIS stands for Institute for Development and Resources in Intensive Scientific Computing, and it's part of the French National Research Center, CNRS. Nathan and Hatim are part of a team that works on Bloom, an open-source large language model used in machine learning and artificial intelligence. Of course, we've heard a lot about large language model this year, including, of course, ChatGPT by OpenAI. But in contrast to the commercial models, Bloom wants to make the model available to a wider public, be that AI practitioners, researchers, or indeed other companies. Bloom has been set up by an initiative called Big Science involving researchers as well as the company Hugging Face, and it has over 1,000 contributors. And the large language model and datasets have been created with the help of the Jean-Zay Supercomputer at IDRIS in Paris-Saclay. Why supercomputers are needed to create and develop large language models is one of the topics I wanted to discuss with Nathan and Hatim. Bloom, of course, is not the only project they work on, because AI and machine learning are being used in a variety of different research areas, like, for instance, medical imaging, and we touched on that briefly too. So here now, my conversation with Nathan and Hatim. Hello, everybody. We're here at IDRIS in the south of Paris. And with me here today is Nathan and Hatim, and I let them introduce themselves. So maybe you first, Nathan?
I'm Nathan, so I've been working at IDRIS for the last 2 years. So I am an artificial intelligence engineer.
Mm-hmm.
At first, I have a diploma in electrical engineering, but then I switched to artificial intelligence when I went in the UK for a master degree. But then I've been working for IDRIS, and it added a new component like high-performance computing, which is very important for artificial intelligence, but which I did not know about before coming here.
And which is why we're talking today. Anyway, okay. Hatim.
So hello, my name is Hatim Bourfoune. As Nathan, I'm a research engineer in artificial intelligence here at IDRIS for the last 2 years, like Nathan actually. I have a background in industrial statistical, I'll say. And then I switched to AI at my first year of working. So I learned by myself AI, and then I did some projects, and then I joined IDRIS.
Can I just ask, out of curiosity, how did you learn AI by yourself?
Yes, so I discovered AI actually at my engineering school.
Mm-hmm.
So we did statistics, and we saw a bit of machine learning there. So it's when I discovered it, and I really liked it. So I kept in my mind that maybe I want to switch in that area. Then when I decided to switch to that area, I did several mock online. I followed the very famous mock of Andrew
NG,
yes,
from
exactly.
California.
So I started like that. Then I did several other mock online, like I can't remember. There was too many.
Yeah.
Then I started to work on project on Kaggle, which is a competition website,
Mm-hmm.
that hosts a competition about AI. And then I apply to PySchool, which
Mm-hmm.
is program that allow engineer, researcher to work on challenging projects on AI, which
Mm-hmm.
was my real, work. And then I joined IDRIS.
Okay. Maybe we can start off with the kind of projects that you're currently working on.
We're working on multiple projects, and it has multiple fields. So currently I'm working with Paris Brain Institute. Basically, one of their team is developing software to allow researchers to use deep learning. It's mostly used for research for the Alzheimer's disease, but
Mm-hmm.
it could be used for, in theory, any brain disease.
Mm-hmm.
And basically, they needed IDRIS's help to speed up their code, because researchers do not have the high-performance computing skills that can be required to not waste time and maybe distribute their code on multiple graphic cards. another project. So this project I've been doing it without Hatim. It's my project. I'm the only one doing it. But we also have a shared project which was about evaluating a large language model, Bloom, which was trained here. And yes, that's the two projects which I've been working on for the last 3 months.
So as Nathan said, I'm working on the Bloom project. So actually the evaluation part of Bloom. And also another project which means to make Bloom easy for researcher, because Bloom, it's a very big model that it's hard to train again, to fine tune. And we try, so with Nathan, to make the fine-tuning part of Bloom easy for some researcher. It's a project that is linked to the evaluation of Bloom. Otherwise, well, recently, so a few months ago, I did Plug AI, which is a project in collaboration with Creatis, which is a laboratory specialized in medical study. And the aim of that was to create a framework that can do segmentation on medical image, easy for people who are not used to use AI or the framework that it needs.
Maybe we can start talking about Bloom. Perhaps you can introduce the project quickly, what that is. There's also an article on Archive, which I'm going to share in the episode notes, but maybe you can give kind of a high-level introduction.
So Bloom is a large language models. Bloom is not the first large language model to be trained, but usually large language models were trained by private companies like OpenAI, Google DeepMind, or Facebook. And they would keep the neural network for themselves. So maybe they would share the topology of the network, but they wouldn't share the weights and what comes out of the training process.
So, the hyperparameters.
They would give the hyperparameters, but they wouldn't give the weights.
Okay.
Which is the most important thing. The issue is that large language models would be only for very big companies, and we wouldn't know exactly how it was trained. And it would also make research about large language model much slower, because many researchers would try to use them, but they do not have access to them. They cannot change them. It does make it very difficult to understand. There are not that many large language models, so it is difficult to understand how they work exactly and why they work. And if you cannot try things to understand, then it makes things even slower. So the idea of Bloom was to have an open source large language model, which would be public, and every researcher could use it, and maybe even any company could use it. And that's the idea of the Bloom project. There are many researchers who worked on Bloom, so there are something like 1,000 researchers, I believe.
A large collaboration, not only in France.
No, it's from around the world, actually. Many institutes or even companies worked on it, and it was trained here on Jean-Zay. We provided the hardware and provided the software, and it ran for like 3 months.
I think you said everything approximately. Yeah. Maybe something that I can add. It's Hugging Face, which is an American company who initiate the project, and they ask IDRIS for the resources, which is the most expensive part. That's why most of companies keep the model for themselves, is because it costs a lot to make that kind of model.
Maybe we can talk about this, what it actually takes to create a model. Nowadays, I assume that you don't exactly start from scratch, do you?
Yeah.
You have some kind of basis.
So to train that kind of model, just the final training part. So I'm not talking about the development, which still needs resources, but just the final training part, it's 400 GPUs for 3 months running continuously. So it's quite a lot. Just the electrical bill about it's tremendous. But there's a development part. Thankfully, Big Science started 2 years after the release of GPT-3. So there was a lot of research about that kind of big model that was made. So Big Science, thanks to that research, they could have a good start. They already have some kind of architecture in mind. So they just reduce the list of hyperparameter to a few things that they tried. And then when they saw which combination of hyperparameter was the best, they just trained it for 3 months.
Can we talk about the architecture of Bloom?
Back in the days, so I'm talking about 10 years ago, which is basically archaeology for deep learning, we would use recurrent neural network. So basically a network which uses its own output as an input. But then some people found a new architecture called transformers, and by stacking them, you would have a very powerful tool to understand the semantic of a sentence, and it could handle very long sentences. And there are basically two kinds of transformers. Either you take the whole sentence, and when you're analyzing a word, you take into account previous words as well as next words. But you also have the most modern version, which only takes into account previous words. It's less information, but in return, it's very powerful to make generating content. When your task involves generation, it's very strong. Basically, the other kind cannot do text generation as well because they require the next words because that's how they were trained and they are used to having access to next words. So you cannot really do text generation with this kind of transformers. Basically, it's good for text analysis. Yeah, the newer large language model, so the GPT kind, which are stacks of what are called decoders. They are very good at generating content. And basically, almost every task can be turned into a generation task. So they can basically do anything.
Can we clarify what we mean by decoder?
The first transformer had two stacks of neural network, and one was supposed to be the stack of encoders and one the stack of decoders. And basically, if you're trying to translate a sentence from French to English, the stack of encoder would take the French sentence and try to understand its meaning regardless of the language. In the middle, you would have a representation of the sentence regardless of the fact that it comes from French. And then you would have the stack of decoder, which would take this representation and decode it in English.
What kind of applications do you have in mind when you think of Bloom?
So Bloom is a large language model, and I like to see large language model like an engine. You can do, how can I say, the application I'll see it has a car, and Bloom will be the engine. So basically with the large language model, you can do almost any application regarding text. So for example, if you want to have a translation task, Bloom can do it. Actually, he's pretty good at translation because he was trained on several languages. Well, you can make a chatbot like ChatGPT with it. You can have a better motor research engine. Yes, anything that can touch to texts.
How many languages does it actually support?
Yeah, I think it's 46 around something. Approximately, it's 46 language that it was trained on. But what's interesting, because we trained it on a large amount of text, actually there was some, even in the French part or the English part, there was some part of the text which was in another language that it was not trained on. And for example, when we did the evaluation, one of the researchers saw that it kind of do some Italian language processing. Pretty good. Not obviously, it's not the best, but it can understand a bit of Italian, even if Italian was not part of the language that it was trained.
The Bloom model, is it currently being used by researchers only, or is it also, you mentioned industry participation, is it also used by companies?
Recently, Sambanova, which is a company that makes hardware, and Together, which is a collaboration of several researchers and engineers, used Bloom to make a chatbot, which is called Bloom Chat. So I think that's the first company that use it, well, of what I know. Yeah. But I know that a lot of researchers use Bloom for either comparison or evaluation or other tasks, yes.
The next thing that I would like to touch on is high-performance computing and at what stage in the process high-performance computing is needed and required for dealing with large language models such as Bloom.
When you're training any kind of neural network, so you're doing a lot of linear algebra, and it was found that GPUs are very, very good at doing that. But then your neural network needs to fit within the memory of the GPU. And yeah, even if the GPU is very powerful, bigger networks cannot be trained on a single GPU. And modern GPUs are very powerful. They have a lot of memory and they go really fast. But large language models, it's just another scale. We cannot train a large language model on a single GPU or very tiny large language model. You need at least dozens of GPUs to train them just to fit in memory and to have your answer, the output of the network within a reasonable amount of time. So Bloom used 400 GPUs. So if and you're not doing a training process as intensive, you can go lower. If you need, you can go even higher. I believe GPT-3 used 1,000 GPUs.
Okay.
Yeah, just for inference, Bloom cannot fit within one GPU if you're using the raw version of the model. So even for inference, you require 8 GPU, if I believe. They are just that big, and there is no way around it.
Okay. Which, of course, is why we're here in IDRIS, which hosts the supercomputer Jean-Zay.
Yes, exactly. A supercomputer like Jean-Zay, it's needed because, as Nathan said, we'll divide the model into several parts, which will be in several GPU. And we need that the connection between those GPUs are very fast. Otherwise, it will take way too long to train. So that's why we need a supercomputer and not something like AWS, which has the number of GPU, but usually the connection between those GPU are pretty slow.
Oh, right. Okay. Well, that's another aspect that I wanted to touch on, because there are now services like AWS, which you mentioned, that offer these kind of GPU services. But we still need these kind of research centers because they still have shortcomings in terms of speed and performance. Is that what you're saying?
I think now AWS propose that kind of services. So several GPUs that are very well connected together, but for a price that will be very,
Yes.
very, very important, obviously. So that's why we need like supercomputer, especially if you do research, for example, in France. You maybe don't have that money to spend.
Well, or
So
anywhere
yes.
else for that.
Yeah.
Matter.
So yes.
The training you mentioned, it takes about 3 months,
Yes.
having a large language model trained. So how do you make sure? Do you wait for 3 months to find out what the outcome is and how the performance of the model is? Or how does this work?
Basically, there is not one Bloom model. There are actually multiple Bloom models and smaller ones. So you start from the smallest, then you gradually increase the size of the large language model. So you can see issue appear by one. And even when you're training the final model, the biggest one, you're still monitoring what's going on. Almost every large language model did find some issues during the training process because maybe the loss, the error was skyrocketing at some point and needed to do some modifications to avoid that. So it is monitored very closely. It's 3 months, but it's also 3 months with a lot of GPUs. So overall, it's 1 million compute hours. So you do not want to waste that. That's why it's watched very closely.
What happens when you do find a problem with it? Do you then stop and start again, or what happens then?
No, actually, the state of the model during the training are saved several times.
Okay.
So when we monitor, when we see that there is a problem, for example, in the loss, we can go back to the previous state that we saved, check what was the problem, handle it, and then continue from that part. Obviously, if we have a problem like at 2 months and a half, it wouldn't be good to just start again. So that's what we are doing.
Okay, so you do monitoring that basically on a daily basis or on an hourly basis or
Yes.
a continuous basis.
Exactly, yes.
How do you measure the performance then?
Well, the performance of the model, right? So after the training, it's actually pretty hard. We need to do a full evaluation, and it's what we are still doing actually. So that kind of model, just for a little history, when the large language model was not that large, so it was a few million or just a bit of a billion, we usually fine-tune the model on a specific task, and then we evaluate that task. So we have a metric score, and then we compare it to other language model that was fine-tuned to that task too. But now the models are very large, so just fine-tuning to one task, it's very costly. Now the usual way to measure the performance of the model, it's by doing what we do, either zero-shot learning, few-shot learning. So actually, it's because it's a generative model, it can generate text, so we can ask to do anything. So we'll ask directly the model to do a task, and we'll measure the metrics. For example, we have a list of review and we want to know if the model recognizes the review to be positive or negative. So we just give him the review and ask him, is it positive or negative? And then see what he generates and compute the accuracy with that output.
The test data set that you actually use, the basis, must be absolutely huge now because you have 46 different languages and text. So where do the data actually come from for all of this? And is this changing continuously?
Yeah, you have 46 languages, and for each language, you have multiple tasks which you want to test. So it could be a sentiment analysis or a summary or anything. So you have a lot of data. Where do they come from? So it depends. So for instance, if you want to do sentiment analysis, it's quite easy because Amazon or IMDb they have big data sets which are perfect for this. If you want to do summary, you can check on social networks. Maybe they can have some things like. Yes, that's a very difficult task, and it's very expensive actually to sometimes do the labeling. So that's why you try to avoid this part as much as possible. And some companies, they have access to a special kind of data sets which they can make public to help the research in this field. So for the multiple languages, what's interesting is that not all of them are common. So obviously there are very common languages like French, English, Chinese, and so on and so forth. But you also have very rare languages, some kind of African languages which are not very used anymore. You do not have a lot of resources on those languages, but they are interesting because you want to know how good the model is to understand a language on which it does not have a lot of data based on the other languages. So you may have common points, and you want to see how is it or how hard it is to understand a new language. So I do not know for all of them, but I assume that test datasets are much smaller, and it is obviously way harder this way to test them. But yeah, there are multiple test datasets. So for Bloom, I don't not know the number exactly, but there are dozens of tasks which are tested.
Okay, maybe we can spend some time talking about your own projects. Plug AI, maybe we can start with that, Hatim. What is it, and how would you describe that?
So it was a project initiated by Creatis. I can say hired me and another coworker at IDRIS, which is Kamel Gerda, to help them to make that tool. The aim of that project is to help researchers and doctors who are not specialized in AI to do segmentation on medical image. The training, the evaluation, all that process, we tried to make it easy for researchers. The aim of that project was also to have one tool that can be used for people who are not used in AI, but also for people who know a bit more of AI but want to use a model that was trained by a doctor who don't know AI but want to modify it a bit. So we had to make it flexible. So that was the aim of Plug AI.
Is that any medical image like X-ray, and then you go to MRI and CT and echo and ultrasound, I mean? Or is that specifically for particular types of medical images?
Actually, it can be made by any medical image, 2D or 3D. So you just need to have the data set. If you have the data set in the right format, it's okay.
Okay, excellent. Nathan, Nathan, I should actually say.
Yeah, so the project which I have with ICM, so the Brain Institute, the software is called Clinica. My part was about making the computation faster and also the software much easier to use, basically because it's a software which is driven by research. Not every features are thought about at the very beginning. It's added one at a time, and sometimes you need to rework the code, so it is easier to do modifications. I'm helping their team do that, and also adding new features about the high-performance computing part, which at IDRIS we know very well. So it could be about doing what's called automatic mixed precision. So instead of doing all the computation with 4 bytes, some of them can be done with 2 bytes, which is much faster and uses less memory. Also, the fact that you could use multiple GPUs will be introduced in the software. Even the simplest way of doing distribution, which is replicating the model on multiple GPUs, but giving them multiple samples of the dataset, can speed up the training process by a huge factor, actually. So I'm working on this software, which also does some pre-processing on a brain MRI.
Okay.
But that's not my part, so I cannot really talk about it much. I'm on the deep learning part.
The high-performance computing bit is something that I would like to talk about. So what kind of frameworks do you use to actually distribute code on different GPUs, and how does this work?
Usually the base framework that we use is PyTorch, which is very known by the community. But for distribution, we use several other tools that are built usually on top of PyTorch to make a distribution more efficient. So we can say, for example, Megatron, which is a tool built on the top of PyTorch and which make parallelism very efficient. And when we say parallelism, it's data parallelism, but also model parallelism. Model parallelism, it's to cut the model into pieces and put it on some GPUs. So we can mention DeepSpeed, which also do some distribution, but in a different way of Megatron. Maybe I don't know if I go into detail about that, but it does what we call the zero, which is a way to cut not the model, but the optimizer states. Well, actually, I think there's a state where he cut the model too, but it's all about splitting the memory usage into several GPU and do it very efficiently. So recently there was Colossal AI, which was released. Its aim is to do what Megatron and DeepSpeed and other framework does, but in a more easy way and a more flexible way, because Megatron and DeepSpeed are not very user-friendly, if I can say.
The final question that I have then, if people are interested in getting into this, you mentioned you learned it yourself with these mass online courses such as Coursera's with Android NG. What would you recommend? How would you start with all of that?
Now, artificial intelligence is very widespread. We talk about it in the media basically all the time. So there are many courses about every type of artificial intelligence on a very famous websites like Coursera or Udemy. You can definitely find what you need, or even free resources, which are very good and give you the theoretical aspect and the mathematical part of the field. Maybe you will not have a very practical usage of deep learning and artificial intelligence. But with the internet, you have an infinite amount of resources, and it is very easy to have at least a base understanding of how it works. And for a deeper understanding, it will take a bit more work, but all the resources are available. And even a few universities do publish their courses. I believe Harvard or Stanford do it. It is a gold mine.
And of course, IDRIS itself has an online course on YouTube, which we're going to share in the episode notes. It's going to be in French, but it's there.
We have multiple courses. So the online one is called Fiddle, but we also have courses which we do here at IDRIS. And the purpose of these courses is the fact that in French, the audience is basically PhDs and doctors in France, which are from many different fields. So maybe if you're a biologist or chemistry, you have never used deep learning, but deep learning is very efficient in some of those fields. So we are teaching them.
The other part, of course, is then high-performance computing, which I think is more specialized, and training opportunities might be a little bit less widely spread as they are for machine learning or artificial intelligence. Hatim.
Yes, actually, the resources about HPC in AI are very rare. Even the documentation of the tool that I mentioned it earlier are not that good. So to learn about it, it's very hard. First, to mention it, here at IDRIS, we provide courses about it. We call it the LOJZ. It's a course specialized in actually high-performance training and inference of deep learning model. In our course Fiddle, we have one session about that actually to software acceleration and hardware acceleration. But except of that, to be honest, I don't know any courses where you can learn the distribution of the model, of the data, etc. Also, to practice that kind of method, you need a lot of GPUs. Well,
and you need access to high-performance computing.
Exactly. And not a lot of people obviously have access of that because it costs a lot, so it's very hard. That's why the courses that we do at IDRIS, I think it's... I don't know any other courses where you can do that actually, because we train the students are working directly with Jean-Zay, so they are trying directly the method that we teach them. So...
Okay, and we're going to look at Jean-Zay next, which unfortunately the listeners can't see, but I will be. Okay, well, thank you very much for your time today.
Well,
that was
thank you.
Very interesting. Thank you.
As I've mentioned just now, after our interview ended, Hatim and Nathan took me downstairs to show me Jean-Zay, the supercomputer itself. Entering the room requires special permission and a set of good earplugs, because the sound of the machine can be deafening. The machinery is of course very impressive, and Nathan and Hatim showed me some parts, like GPUs and other goodies. It was a great and impressive tour, and I'd like to thank both for their welcome and their time. There is, as I mentioned as well, a lot of excitement in the air around artificial intelligence and machine learning at the moment. As Hatim mentioned during our chat, there are plenty of courses for you to choose from, including the now legendary one from Andrew and G at Coursera, which is still running and ever expanding. Getting into high-performance computing, on the other hand, is not quite so straightforward, because for one, it's a question of access and being able to work and learn on one. There are a few courses available, usually run in computing and research centres. In the UK, the Universe HPC project is working to provide pathways for teaching, learning and education. If you happen to be in France, there's a great YouTube channel called Fiddle. You'll find the link in the episode notes along with other links. And finally, for those wondering who Jean-Zay is, or rather was, and why a supercomputer was named after him. Jean-Zay was the Minister for Education and Fine Arts of the Third French Republic during the 1930s. He was imprisoned by the Vichy regime during the Second World War and assassinated in 1944. His political convictions and his contributions to national education earned him a place in the Pantheon in Paris in 2015, and it got his name on a supercomputer just a few years later. And with that, goodbye. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.